Hey class, Adam Ward here. I want to work through an exercise that's a Darcy's Law application in 2 dimensions. So what we're looking at here is an unconfined aquifer. We've got different hydraulic conductivities in the horizontal and vertical, or x and z dimensions of the problem. We're given a porosity of 0.3. And we're going to work on 2 problems. First, what are the x and z directed component fluxes and magnitudes? So if we have flow moving both in the x and the z dimension, let's analyze those individually. And then part 2, let's look at the overall direction and magnitude of flow. In other words, rather than separately considering the components, let's put those 2 together. Okay, so first let's take a look at the gradients. Excuse me. dH dx, so the x-directed hydraulic gradient. We can see that we were losing 7 feet if we moved 500 feet in the horizontal. And so we get an x-directed gradient of 0.014 feet per foot. Notice that's negative because we were losing head as we moved in the x direction. Similarly, in the blue pen here, I'll work through the vertical hydraulic gradient, minus 10 feet per 100 feet. And so in that case, we've got a gradient of 0.10 feet per foot. Now with the gradients in hand, we can grab Darcy's law, and I'm choosing the specific discharge version here, minus kx, the x-directed hydraulic conductivity, multiplied by the hydraulic gradient in the x direction. So I'm grabbing hydraulic conductivity, which we were given, 1 times 10 to the minus 5th feet per second. And you can see I'm pulling that hydraulic gradient down from our calculation above, and I get a value of 1.4 times 10 to the minus 7th feet per second. That's specific discharge, not velocity. And we can do the same thing in the vertical dimension here, paralleling what we just did in the horizontal, grabbing that hydraulic gradient that we've previously calculated, and we can get a specific discharge of 1 times 10 to the minus 7th feet per second. So we've got our gradients and we've calculated our component discharges as requested in the problem statement. Next step is to put this all together. And so I want us to think about this just like in a calculus class where we might be adding vectors together. We've got a qx and a qz shown in black and blue, and the resultant vector q shown in orange. So first, what is the magnitude of that resultant vector q? We can use right triangle geometry, Pythagorean theorem here, plugging in the qx and qz values that we calculated on the previous slide. We can readily solve for that resultant magnitude of about 1.7 times 10 to the minus 7th feet per second. So well, in black and blue, you're talking about or thinking about how fast about the discharges in the ordinal directions, x and z. That q is not moving along one of those axes. It's moving in a different direction, and it's moving faster than either component. That makes sense to us because the hypotenuse of that triangle should be longer than either one of the 2 legs. How about the direction of flow? Similarly, right triangle geometry is our friend. And so I'm labeling the angle theta in green. We can solve the tangent of theta is the opposite over the adjacent. And so qz over qx. Plug those values in, take the inverse tangent, and I get a theta of about 35.5 degrees. So now we've got the magnitude and the direction. There's one extension I'd like to show you in this problem, and that's how we could address it if we decide to solve in matrix form. So the 2 equations that we had written out for qx and qz, we could combine those. So think back to sort of a linear algebra approach here, where we could take the hydraulic conductivities and we could put those in a matrix, and then we could take the hydraulic gradients and put those in a matrix. So just to be explicit about it here, kx and kz, you can see I've labeled in orange, and dH dx on top, dH dz on the bottom. So q's equal minus k's times hydraulic gradients, dH d blank. And I'm using a blank there because the top one is the x direction and the bottom is the z. So just a friendly reminder, if you haven't been doing matrix math for a while, what we've just set up here is a matrix that looks like what I've shown here in blue, capital A and B equal that matrix of tensors A, B, C, D multiplied by the forcing function there, x and y. Now the way that multiplication of matrices works, you might remember, is rows times columns plus rows times columns. So RC might be something that was stuck in your head from a linear algebra class. And so we can take that matrix math and we can extract the individual equations back out of it. But when we do, we find what we find here for our Qx, for example, is that we do have that minus kx dh dx term, but then we have this second term, 0 times dh dz. Right? And so what's with the zeros? Where did that come from, and what does that actually mean physically? Is that an artifact of putting this into matrix form, or is that something that we might either have to cope with or alternatively take advantage of? So first, let me highlight this 0 that was in the top right of our hydraulic conductivity matrix. You can see I've pointed purple arrows at that location throughout the slide. Now, what that strictly represents is what we would call KXZ. Those subscripts meaning it's a hydraulic conductivity in the x direction that is realized when you have a gradient in the z direction. So it's an x-directed flux due to a z-directed gradient. Similarly, the ones I'm pointing yellow arrows at would be KZX. This is a z-directed flux due to an x-directed hydraulic gradient. And the reason that we're teeing these up and looking at these off-diagonal terms is this is where anisotropy will show up in our problem sets. In other words, this is part of the manifestation of what's going to happen to us when we have different hydraulic conductivities in different directions, and they're not perfectly independent of each other. In other words, if we push in the x direction, we might get a little bit of bleed over that causes a z-directed flux. So that's teeing us up for a discussion of anisotropy and how we deal with it in terms of matrix solutions. That'll be the next topic that we're covering in lecture. So hopefully this example problem was useful, and you can start to see where some multidimensional complications or opportunities come into our problem set.